This is lesson 3.8 on vertical asymptotes. For these next three sections, so 3.8, 3.9, and 3.10, we are going to be working with functions that are known as rational functions. A rational function, that's what you get when you divide two polynomials. One of the characteristics of rational functions is that they're known for having asymptotes. There are three types of asymptotes: vertical asymptotes, horizontal asymptotes, and oblique or slant asymptotes. And those are going to be what we talk about these last three sections. Now, asymptotes, these are lines that the graph is going to get closer and closer to. Some of them we're allowed to cross, some of them we aren't, but in general the term asymptote means something that we get closer and closer to. Now, today's focus is going to be on the first of those asymptotes, vertical asymptotes. When we have a vertical asymptote, that's going to be a vertical line that the graph gets closer and closer to, but this is one where it's actually never going to cross it. So as the function gets closer and closer to that line, it's going to get very, very, very big in the positive or the negative direction. We will sometimes say that our function approaches infinity or negative infinity as our x value gets closer and closer to this vertical line. In our rational functions, we're going to find the location of these vertical asymptotes by looking at zeros in the denominator. So remember, rational functions, that's the quotient of two polynomials. We're going to look at wherever the bottom part is 0, and if it's not canceled with a similar term in the numerator, that's going to be where we have a vertical asymptote. Now, if we have a term in the denominator that gives us 0, but we also have the exact same term in the numerator, they're going to cancel out. They're still going to have an effect on what our graph looks like. It's going to leave a hole at that point. But if the terms cancel out completely between the numerator and denominator, it's not going to result in an asymptote. That will only occur when there's an uncanceled 0 in the denominator. So here's a drill problem that we'll see from this section. So locate the vertical asymptotes and holes of this bad mamma jamma right here. So this is an example of a rational function. This is a rational function where everything has been factored out already. For the drill problems, once again, really for just about all the problems we're going to see here, I'm going to go ahead and give these to you already factored. I do want you to be able to factor. We will have problems where factoring polynomials is the point, but here I want us to get down to really to business with the rational function. So we will see these already factored for us. So what we need to look for is we need to look at the denominator. Wherever the denominator is 0, that's really where we want to look at. So look at the denominator, look at the locations of the zeros. So we have this x plus 2 term, so x equals negative 2 is going to be a location where the denominator is 0, and x minus 1, so x equals 1, that's going to be the location of a 0 in the denominator. Now notice, x plus 2, that's what gave us the x equals negative 2, 0. There are no x plus 2 terms in the numerator, so we know that this is going to give us a vertical asymptote. I'm going to use VA as a shorthand for vertical asymptote. X minus 1, that's what gave us the x equals 1, 0. Notice we have an x minus 1 squared term in the bottom and an x minus 1 squared term in the top. So these are going to cancel. These are not going to give us a vertical asymptote. Now, one small but important distinction. When we cancel these out, that's going to make the function look like this. So we're left with just the original terms. Now here's the weird thing. This function that I've written here is not the same as this function here. You might wonder, well, why not? Because we just cancel out two things. Why shouldn't it be the exact same thing? It's a minor but very important distinction. This original graph, remember, it was not defined at x equals 1. At x equals 1, we divide by 0, and that is always bad news. It doesn't matter what the numerator is. If we're dividing by 0, we don't like that. So we're not even going to calculate what happens there. Whereas this function, at x equals 1, who cares? Nothing bad's happening at all. So these are going to look exactly the same everywhere except at x equals 1. So what that means is for the original function, we are not able to define the function here. So that's actually going to be the location of a hole. And so this is our answer. We have a vertical asymptote at x equals negative 2, and a hole at x equals 1. That's it. That's all we do for these problems right now. We want to locate the vertical asymptotes and the holes of the original function. The vertical asymptotes are from all of the uncanceled zeros in the denominator. Holes are from the fully canceled zeros in the denominator. So x plus 2 was not canceled, so it gave us a vertical asymptote. X minus 1 was completely canceled, but it still affects the whole function, so it's going to put a hole in the graph at x equals 1. All right, here's one more. So locate the vertical asymptotes and holes of y equals 5 times x plus 3 squared times x minus 2 over 4x squared times x plus 3 cubed. Okay, so once again, we're going to look at the denominator. Find where the denominator is 0. So 4x squared, actually just x squared is what we focus on here. That x squared is going to be 0 when x equals 0. So there's one of the zeros in the denominator. And x plus 3 cubed, that's going to give us a 0 of x equals negative 3. Okay, x squared, I don't see any x squared terms up top, so that means that x equals 0 is going to give me a vertical asymptote. All right, x plus 3, here I have x plus 3 cubed, here I have x plus 3 squared. They're not the same, so we have to be careful here. If the degree down below is bigger, that means that this is not going to be fully canceled out. We'd get rid of all the x plus 3 terms up top, but we'd still have, in this case, a single x plus 3 term remaining. So if the degree down below is bigger, that means we're still going to have a vertical asymptote. If the degree up top is bigger, that means we're going to have a hole at that location. So here, since the bottom is bigger, we're going to have another vertical asymptote at x equals negative 3. So our answer here is we have vertical asymptotes at x equals 0 and x equals negative 3. I'll go ahead and put it in order. So that's our answer. Now just a side note, we're going to return to this idea when we get to the very end of this section. We're going to talk about sketching the graphs of rational functions. And once again, it's an honest-to-goodness sketch. So what we would do here is we want to talk about what's happening at x equals negative 3 and x equals 0. So I'm going to mark out 1, 2, 3. So that's about the location of x equals negative 3. When we sketch our graph, what we're going to do is wherever we have a vertical asymptote, we're going to put a dashed line in that spot. Remember, x equals negative 3, that describes a vertical line. Similarly at x equals 0. Here it's going to be hard to see over the y-axis, but that's okay. We still put a dashed line along x equals 0. So be mindful of this. What this means is that our graph, when we graph it, and again, we will look at more information about how to determine whether it goes up or goes down. Who knows? We'll get to that later. But what our graph is going to look like is it's going to get closer and closer to this line, but not actually touch it. It's going to get bigger and bigger. Similar story down here. We're not going to touch these lines. We're going to get closer and closer to them, though. Here it's going to get bigger and bigger in the negative direction. That's a terrible graph, sorry. Maybe same idea over here. Our graph's going to get closer and closer to this line, but not touch it. It's going to keep getting bigger and bigger in the negative direction. So a vertical asymptote, our graph gets arbitrarily large. It's going to get closer and closer to infinity, which is what the graph is doing here, or closer and closer to negative infinity, which is what we're doing here. That's actually not quite true, this idea of getting closer and closer to infinity. You never get to infinity. When we say that, we just mean it's getting bigger and bigger and bigger and bigger. Think of the biggest number you can think of, and the graph just flies right by it. There's no stopping how big it gets. That's what we mean when we approach positive or negative infinity. So that's what our graph does here. The vertical asymptotes just show us, hey, this is where the graph just blows up. We'll take a look at this later on about what steps we need to take to give a more accurate portrayal of our graphs here. It's a fairly involved process, but we need to talk about our other two types of asymptotes before we spend much time with it.